One of you asked me last class that the positive and the negative sign of the wave function. How is it obtained? It comes from the quantum mechanical calculation. It does not come from experimental data. Only when you do the calculation shows that one has to be positive, the other has to be the opposite of positive, that is negative. Okay, to get the minimum energy. So now halides again can be classified into two categories. Group 1 to accept beryllium, alkali metals in general they form the ionic compounds. Although lithium has some covalent character, but not appreciable. But among the alkali metal, lithium has some appreciable some amount of covalent character in halides. For example, lithium chloride. Lithium chloride is soluble in alcohol to a great extent, unlike sodium halide chloride or potassium chloride or rhodium. That indicates that some amount of covalency has been introduced in the halide. The another example is that if you look at lithium chloride, lithium bromide, lithium iodide.
Excuse me, sir.
Yes?
Sir, you said that LiCl is soluble in alcohol. So
Yeah.
how does it indicate covalent character?
Because non-polar solvent, so non-polar will dissolve in polar solvent. Ionic compound will dissolve in polar solvent. So the polarity in alcohol is less than that of water. Now another example, what I will give you right now, is that where the ionic character remains the same. Higher the molecular weight, higher is the melting point. Okay. For example, if you look at okay. Beryllium chloride has substantially lower melting point than the other halides, group 2 halides. Now, how do you account for that? Okay, the molecular weight is not changing dramatically. Beryllium atomic weight is 9. Okay, magnesium 24. So this is not a large difference in atomic weight. Chloride is common, but there is a difference in 300 degrees Celsius difference in melting point. So when you see that a drastic change in melting point, that is an indication that the covalency is responsible for lowering of melting point. Since beryllium has the smallest size, so charge to size ratio will be maximum, polarizing power will be maximum, so the tendency to form covalent compound will be maximum. As a result, the melting point will decrease. But these three, magnesium chloride, calcium chloride and barium chloride. Can you read what I am writing on the board?
Yes.
All three are ionic compounds. Okay?
Yes.
All three are ionic. Their polarizing power is not very large. The chloride is not a highly polarizable anion. Polarizability comes from low electronegativity, greater size. So chloride electronegativity is not very low and the size is not very large. So the magnesium chloride, calcium chloride and barium chloride, they are all ionic. But look at the melting point. It keeps on increasing. So when the ionic character does not change, the melting point increases with increase in mass. So there is an increase in melting point with increase in molecular weight. When the ionic, all are ionic. Now, if you look at lithium chloride, lithium salts, lithium iodide has the least melting point. For example, if you look at lithium chloride is 613 degrees Celsius. Lithium bromide, lithium iodide is 469. So here, the lithium has some polarizing power, and as we go down from chloride to bromide to iodide, the polarizability increases,
Yes.
electronegativity decreases, as a result the covalency increases. And I said normally covalent compounds will be low melting. Normally.
Yes.
Because there are covalent compounds which are very high melting. Diamond is the highest melting point, which is a covalent compound. Quartz is a high melting point, which is a covalent compound. Silicon dioxide is a covalent oxide. Graphite, okay, it is a covalent compound. It's a covalent graphite, but it's a polymer. It's not a three-dimensional network structure, but it forms a polymer, two-dimensional. So when you have a network structure and a polymer, or a polymer with a two-dimensional structure, it will lead to high melting point, even if it is covalent. But if it exists as an individual molecule, then the increase in covalent character will lower the melting point, and that is what you can see here, that lithium is common, chloride to bromide to iodide. As I go down, the melting point is decreasing. Lithium iodide is having the lowest melting point among the alkali metal iodide. Similarly, the other metal halide, when the metal is in not very high oxidation state, it is limited to 2 maximum. That is what I say lower valence, +1, +2. They will form an ionic compound, halide. For example, zinc chloride, nickel chloride, ferrous chloride, copper chloride, they are all ionic compounds. Because the oxidation state is not very high. But another example, if you can see that zinc fluoride versus zinc chloride, 872 versus 275. Zinc fluoride, zinc is common, fluoride is light, fluorine is lighter than chlorine.
Yes.
But zinc fluoride has a much higher melting point than the zinc chloride. That means zinc chloride is more covalent. Lowering of melting point is an indication of increasing in covalent character. So since fluoride is most electronegative, so zinc fluoride will be ionic, and chloride is not most electronegative. So the zinc can polarize the electron cloud of chloride, and as a result, zinc chloride has some additional covalent character and has lowering its melting point by about 600 degrees Celsius. And how do I know this? How do I know that they form ionic halide? Because they are conductor in the molten state. If they are not conductor in the molten state, they are not ionic halide. The covalent halide are formed by higher valent metal halides and groups 13 to 18. They form the covalent halide. So all non-metallic halides are covalent halides. And the metal in a high oxidation state also forms covalent halides. For example, aluminum chloride, now here you can see that the left-hand column I have written, where the oxidation state of the metal is either 3 plus or 4 plus.
Yes.
Whereas the right-hand column is only 2 plus, but still they are covalent. Okay, why? Because in this case the covalency arises due to small size of beryllium ion. But what about mercury? Mercury is not small. So why mercury chloride is covalent?
Electronic configuration.
What electronic configuration? Okay, you have identified the electronic configuration correct. Now you have to expand it.
D orbital is phase and 4s2.
Now mercury chloride, I told you among the electrons, S, P, D and F electrons, the S electron and P electron, they shield the nuclear charge more effectively than D or F electron.
Yes.
And F electron is the least effective electron to shield the nuclear charge. So the 4F14, that the 14F electron is primarily responsible for your increased effective nuclear charge. Increase in effective nuclear charge increases the polarizing power. As a result, mercury shows overlays. They are in a high oxidation state. Aluminum chloride, clean stannic chloride and late tetrachloride. They are in a high oxidation state, so I can apply ionic charge to size ratio concept to explain the covalence. But I cannot apply the ionic charge to size ratio for mercury chloride because mercury is not very small and the charge on the mercury ion is only +2. That means when I can't use the ionic charge, I have to use the other alternative, that is the effective nuclear charge. So the effective nuclear charge, A on mercury, you have 14F electron and you have a large number of D electrons all together increases the effective nuclear charge on mercury so high that it becomes covalent. Where I will use ionic charge, where I will use effective nuclear charge. I will give you two examples. This is magnesium chloride is a solid. It has a melting point 712. Titanium tetrachloride is a liquid. It melts at minus 25 degrees. Size chloride is common. Size is similar. But what is different? The ionic charge. Titanium is 4 plus. Magnesium is 2 plus. So the charge to size ratio in titanium is higher. So makes it more covalent, lowers the volume. In the second case, the charge is the same, class 1, size is same, anion is same. But then,
D10 configuration.
D10 configuration. So sodium is not a transition element, whereas copper is a transition element.
Yes.
So the 10d electron, due to imperfect shielding by the 10d electron, the effective nuclear charge increases. And I told you, increase in effective nuclear charge increases the polarizing power. So
Yes.
the covalency increases. So the two effects can be there to make a compound to be covalent, halide to be covalent. One, increase in polarizing power, and the second is increase in polarizability of the anion, provided the cation has a good polarizing power. Second point is very important. Only size increase of the halide ion is not going to increase the covalency. Sodium chloride, sodium bromide, sodium iodide, all are ionic. Iodide is more polarizable than bromide, bromide is more polarizable than chloride. But all are ionic. Why? Because sodium has not good polarizing power. So it could not deform the electron cloud of the iodide ion to itself, leading to covalency. So only polarizability is not important. Polarizability of the anion and the good polarizing power of the cation will lead to covalency in the compound. And what is the proof that they are covalent? Because they become non-conductor even in the molten state. So even in the molten state, the covalent halide will not conduct electricity, unlike ionic halide, which will conduct electricity in the molten state. Silver chloride, silver bromide, silver chloride, silver fluoride. Two things are happening here. The electronegativity decreases, size increases. That means polarizability increases.
Yes, sir.
And silver has a good polarizing power because silver has how many d electrons? Silver plus has how many d electrons?
10.
Not 10.
10.
Not 10. Silver has 3d10, 4d10.
20.
You can't fill 4d before filling 3d. So silver has a good polarizing power. As a result, you see, the silver fluoride is the only fluoride which is ionic. As a result, it is soluble in water. But the solubility decreases from chloride to iodide. Silver chloride is more soluble than silver bromide. Silver bromide is more soluble than silver iodide. What does it mean? That means if the solubility in a polar solvent decreases, that is an indication of covalency. So silver iodide is more covalent than silver bromide or chloride.
Yes.
So here I am showing the polarizability effect, and also it requires the polarizing power of the cation. Only polarizability of the anion is not going to make the covalence. Then all alkali metal halide would have been different. But all alkali metal halides are ionic in nature. Group 2 metal carbonate. The thermal stability of group 2 metal carbonate. What is meant by thermal stability? That metal carbonate, when I heat it, it should convert into metal oxide and carbon dioxide will be evolved. Higher the thermal stability, if the metal carbonate is more stable, then you require more temperature to decompose.
Yes.
So is actually thermal stability is a reflection of decomposition temperature. Higher the decomposition temperature indicates the metal carbonate is more stable. Now, this can be explained in two ways. What is the order? Order is beryllium carbonate stability is less than magnesium carbonate, is less than calcium carbonate, is less than barium carbonate. That means the barium carbonate is more stable thermally and barium carbonate is thermally least stable. That means at the lowest temperature, barium carbonate will decompose to barium oxide and carbon dioxide. Whereas for barium carbonate to decompose, I require a very high temperature. What makes this? Why this is the order? So the one way of looking at it is crystal packing efficiency. In a crystal, how the cations and anions are packed, how efficient. If they are packed very efficiently, then the decomposition temperature will be high. If the packing is less effective, it will not be stable and it will decompose easily.
Yes.
So, carbonate ion is large in size. So the carbonate ion when it touches each other, form a closed back structure by the carbonate ion. The hole which is created is large. Suppose you take 6 marbles. Smaller size marble, you touch each other. What is the size of the hole? Small. But if the marble is large in size, the whole size will be large. Now as a result, what will happen? Since the carbonate ion is large, so the hole it will create due to crystal packing will be large. As a result, the small cation will have empty space, free space to move in to the hole. So it will go inside, come out without fitting it tight. So it will lead to crystal in it, lattice deficiency, or lattice, the packing efficiency will be less. As the size of the cation increases, the whole size matches the ionic size of the cation, then the cation fixes, mets into the hole, sits into the hole very tightly, and the packing efficiency becomes higher, and that is why the thermal stability becomes higher, decomposition temperature becomes higher. So the beryllium being smallest, it will have the least packing efficiency, and the packing efficiency order increases with increase in size. And when we reach barium, it hits the size of the hole created by the carbonate, and so its decomposition temperature is matched. Second is from thermochemistry. The same concept, the small anion will favor a small cation, large anion will favor a large cation to pack it with. So, well, how thermochemistry can help me to explain their behavior? The thermochemistry, from the thermochemistry I can say, which metal oxide will have maximum enthalpy of formation? Which metal oxide will have a maximum enthalpy of formation, heat of formation? All oxides are ionic oxides. All oxides are ionic oxides of group 2. Okay? So what is the interaction between, nature of interaction between a cation and oxide ion? Ionic interaction?
Yes.
And what is ionic interaction? Electrostatic interaction?
Yes.
In ionic compound you have electrostatic interaction which is proportional to Z1, Z2 by R square. Z1 is the charge on the cation, Z2 is the charge of the anion. So charge of the cation and anion both same for all alkaline earth metals. But what is carrying? The R. What is R? Interionic distance. Interionic distance between metal ion and the oxide ion. As the size of the cation increases, the interionic distance increases, electrostatic force of attraction decreases because it is inversely proportional to R. So as the value of R increases, the electrostatic force of attraction decreases. As a result, the heat of formation of metal oxide will be low. So which metal ion will give me the highest heat of formation? Beryllium oxide. Beryllium oxide will have the least value of R. So the beryllium and oxide ion will have closest to each other. As a result, the electrostatic attraction between cation and anion will be maximum, and that will be reflected in the heat of formation. So the higher the heat of formation, higher is the E arc for reaction going to the left to the right. Because if this is favored, if the formation of metal oxide is favored, then the metal carbonate would like to go to the metal oxide more easily. And
Yes.
since beryllium oxide has highest enthalpy of formation, so the beryllium carbonate would like to move to formation of metal beryllium oxide by decomposition. Whereas beryllium oxide will have the least delta HF value. So the carbonate to oxide formation is not energetically favored. So it requires a very high temperature to decompose to move the reaction to the forward direction. Is it clear?
Yes.
Higher the heat of formation, the tendency to form oxide increases.
Yes.
That means the decomposition of metal carbonate is favored. That means at lower temperature, metal carbonate will change from carbonate to oxide, because by forming metal oxide, I gain heat of formation. Then we go to metal hydroxide. Among metal hydroxide,
Excuse me, sir.
among the metal hydroxide,
Excuse me, sir. Sir, please once more explain that ionic interaction between oxide.
the ionic interaction becomes stronger as the interionic distance decreases, having Z1 and Z2 same. Z1 represents the charge of the cation, Z2 represents the charge of the anion. So in group 2 of metal oxide, the charge of the cation is positive and oxide has -2. So Z1 and Z2 are common. What is changing between the metal oxides of group 2 is the value of R. The R value is smallest for beryllium oxide. R value is the largest for barium oxide. Since as the value of R increases, the electrostatic attraction decreases. As a result, the enthalpy of formation becomes less. Since the enthalpy of formation is less, so the arc for the metal carbonate to go to metal oxide will be less. As a result, you have to force the reaction to move to the forward direction by giving high temperature, heating at a high temperature. Whereas beryllium carbonate, since beryllium oxide is energetically favored, the formation of beryllium oxide is energetically favored, so the oxide formation is favored, and oxide can be formed from carbonate by heating. So the carbonate will most easily decompose to give you metal of beryllium oxide.
Yes.
Among the metal hydroxide, greater the ionic character, that higher is the thermal stability. And greater the ionic character, higher is the basicity. Cesium hydroxide is higher, stability is higher than sodium hydroxide or potassium hydroxide.
Yes.
Why? Because cesium has the lowest ionization energy among the alkali metals. So it will very easily lose the electron and the electron will go to the hydroxy group to the hydroxide ion. Since cesium has the lowest ionization energy, so the charge separation will be maximum in cesium hydroxide, and greater the charge separation, higher is the thermal stability because of electrostatic attraction. And second is, since the hydroxide, the electron is flowing from metal to hydroxide. The electron movement from metal to hydroxide depends on ionization energy. Lower the ionization energy, more electron will be more easily the electron will move to the anion. So, greater the electron density on hydroxide ion, higher is the basicity.
Yes.
So, cesium hydroxide is the strongest base among the alkali metal hydroxide. Similarly, if we look at beryllium hydroxide versus barium hydroxide, group 2 hydroxide or basicity order same. As we go from beryllium to magnesium to calcium to barium, the ionization energy decreases. So, more easily the electrons are flown from the beryllium group 2 cation to hydroxide ion. So, which will have the highest electron density on oxygen atom in metal hydroxide, in group 2 metal hydroxide? Barium hydroxide. Barium has the lowest ionization energy, so it will lose the electron most easily, and it will go to the hydroxide ion. Higher is the electron density, higher is the basicity. Higher the electron density, higher is the thermal stability.
Excuse me, sir. Sir, I am not getting the reason for the stability.
Stability is a charge separation. Greater the charge separation, greater the ionic interaction. Greater the ionic interaction, the higher is the thermal stability.
Sir, if the charge separation is larger, then the ionic interaction would be in turn less.
Distance-wise larger, but the charge separation, two aspects are there. One is the charge separation, another is the interonic distance. So the charge separation wise, cesium will give boost easily. The alkali metal which gives electron on shining light is the cesium. Cesium gives photoelectron. What is meant by photoelectron? When you shine a light on the metal, the electrons are ejected. Not from any other alkali metal. Why? Because in cesium the electron is most loosely attracted by the nucleus. So as soon as you come in quantum energy, the electron nucleus attraction is overcome and the electron is rejected. So the thermal stability is a measure of ionic character. Greater the ionic character, so it is not only the distance, it is the amount of charge which is displaced from the cation to the anion. That is also responsible. So since two effects are opposite, distance is increasing, but at the same time charge separation is also increasing. Now, charge separation is becoming more dominant than the increase in distance. Okay, I give you an example. How two effects can be pointing in two different directions. If we look at the ionization energy of iron, cobalt, nickel, D6S2, D7S2, D8S2. Their ionization energy is very similar. Should it be similar? The number of d electron increasing. Nuclear charge is increasing. Iron 26, cobalt 27, nickel 28. Number of d electron is increasing, so the effective nuclear charge is increasing. Electron nuclear attraction should increase. Okay? So the ionization should increase. But if the ionization is just rather increasing, it's so slight decrease. That means there is another effect must be played. And what is that effect? The electron-electron repulsion. As you add more number of electrons in a small size cell, 3D cell has 3D has the smallest size among the 4D, 3D, 4D, 5D. The 3D has the smallest size. Because n is the size of the cell. N, principal quantum number, determines the size of the cell. Since n is equal to 3 for iron, cobalt, nickel, so the size of the 3D cell is minimum. And as the larger number of electrons are accommodated in a small size cell, what will happen? The crowding will take place. The electron-electron crowding will lead to repulsion because they are negatively charged. So here, the effective nuclear charge is increasing. At the same time, the electron-electron repulsion is also increasing. Okay?
Yes.
As a result, when these two effects neutralize each other, you see the constancy of ionization energy. You don't expect otherwise. You should expect ionization energy to increase as the number of d electron increases because of the imperfect shielding by the d electron. Effective nuclear charge to increase. Increase in effective nuclear charge will increase the electron nucleus attraction. As a result, ionization energy will increase because ionization energy is the energy required to overcome the electron nucleus attraction.
Yes.
But it is not happening so. As a result, there must be some other effect which is opposing the effect due to increase in effective nuclear charge. Increase in effective nuclear charge stabilizes the electron. But there must be another effect which destabilizes the electron, and that is the electron-electron repulsion. So you see, in chemistry, it is not only one effect which always you can't use the same argument everywhere. No. You can't change the experimental result. Ionization energy is an experimental value. Okay? It is experimentally determined. You can't change it. So your argument has to be in a way that explains the observed facts. And that is where you have to use your own judgment. When you come to hydride, after that I will come to solubility, and again you will see how difficult it is to predict the solubility. Okay, the reason I will tell you. The metal hydride okay, not metal hydrides, I will write hydrides. Hydrides can be classified into three categories. Three types of hydrides are observed in chemistry. Ionic hydride, covalent hydride, and interstitial hydride. Ionic hydride, where you have the metal ion and you have the hydride ion. And how do I prove that in ionic hydride the hydrogen exists as H minus? Because
Alkali always exists as H plus.
if ionic hydride, if you melt it and electrolyze it, what will you get? You get hydrogen at the anode.
Hydrogen.
Since I get hydrogen at the anode,
Is oxidized.
that means what type of reaction takes place at the anode?
Oxidation.
So 2 hydride ion gives hydrogen plus 2 electrons. And the metal ion picks up the electron. Say if it is a divalent metal, so it will be 2H2 plus 2 electrons will be metal at the cathode. So the evolution of hydrogen at the anode indicates, first of all, it is a conductor in the molten state, so it is ionic in nature. The second, it is hydrogen is evolved at the anode, not at the cathode. That indicates that hydrogen must be existing in the form of H minus ion. And second, the ionic hydrides they are solids. They are used as fuel because they liberate hydrogen. And hydrogen is a fuel. Okay, hydrogen combines with oxygen into water and with liberation of energy.
Yes.
So, how it can give hydrogen? There are 2 processes by which it can give hydrogen. One, besides electrolytic process, that if I heat calcium hydride, which is known as hydrolyte. Calcium hydride is a useful source of hydrogen. Calcium hydride on heating gives calcium plus hydrogen. Again, it's an electron transfer reaction. Hydride gets oxidized to hydrogen, calcium gets reduced to calcium. Another, if I add water to calcium hydride, the water can be represented as H and OH minus.
Yes.
So, 2 hydride ion will combine with 2 moles of water to form 2 moles of hydrogen gas. And 2 hydroxide ion will combine with calcium ion to calcium hydroxide. So what the army does, the army carries calcium hydride solid, and whenever they require hydrogen, they just add a little bit of water, and immediately the hydrogen is evolved. And that is why the ionic hydrides are useful as a solid fuel. They are solid, they are used as a fuel, so they are useful as a solid fuel because they liberate hydrogen readily. Whereas covalent hydrides are non-metallic hydrides, are covalent hydrides. Why non-metallic hydrides are covalent hydrides? Why non-metal forms covalent bonds rather than ionic bonds? Because they have high electronegativity. Because of the high electronegativity of the non-metals, they do not want to lose the electron, but they want to share the electron and leading to covalence. So the high electronegativity of non-metals is responsible for covalent character. Now, so we can say that group 13 to 17, they form covalent hydride. That includes metal as well as non-metal. Aluminium hydride is a covalent hydride. Boron hydride is a covalent hydride because boron is a non-metal. But aluminium is a metal. But aluminium has a large polarizing power. And hydride ion has a large polarizability. Highly polarizable. When I say highly polarizable, must be charged, the size must be large.
Yes. Yes.
Okay. Can you predict the size? Do you know the size of hydride ion? Can you guess what will be the size of the hydride ion?
The size of that another atom.
Hydride ion is greater than bromide ion, less than the hydride ion is greater than bromide ion, less than iodide ion. Can you guess it? Okay? Fluorine, chlorine, bromine. Bromine is a fourth period. Iodine is a fifth period. Hydrogen is the first period. Why hydride ion is so large?
Low electron, low charge.
One more electron in the smallest size, 1s orbital. You have in the nucleus, you have only one proton.
One proton.
And you have small size of 1s orbital. And you are putting 2 electrons together. Due to extra electron. So the repulsion will be tremendously large. How do you minimize the repulsion? By inflating its size. You increase its size so that the 2 electrons can be separated to a larger distance, minimizing the repulsion. As a result, the hydride ion size is so large. Since the hydride ion is so large and the electronegativity is low, so hydride ion will be highly polarizable. Covalent hydrides could be acidic, neutral, and basic. Basic ammonia, phosphine, they are basic hydrides. Neutral, methane, water, they are neutral hydrides. Acidic, except hydrogen, except oxygen of the 16th subgroup.